Have you ever wondered how it is that we can determine exactly how much energy food actually has? Well, the answer comes from understanding the enthalpy of reactions. Alright, so in our last lecture, we defined enthalpy. We gave it a symbol, we called it delta H, and it was defined as the heat transfer in a constant pressure process. So the enthalpy change for any chemical system is really just known if we know how much heat was transferred in or out of that system. And so what we'd really like to know now is how can we go ahead and measure these enthalpy changes for chemical processes? These are going to be really important because we defined what energy was all about. It was all of the kinetic energies and potential energies of all of our particles, and that is incredibly useful information when collected on a particular system that we're interested in. So we'd really like to know what the enthalpy change is for a chemical system, and particularly as it's undergoing chemical change. So that is the enthalpy change for a reaction. So how are we going to measure this? Well, we're going to make use of something we defined last class as the first law of thermodynamics. And the first law of thermodynamics, of course, says that energy can't be created or destroyed, it can only be transferred. Now, we can make use of that by defining something called a system and something called the surroundings. So imagine we've got some container, some vessel, and this is our system. Maybe there is a gas inside, maybe there is a solution inside. At this point, it doesn't matter. Everything else on the outside of this system is known as the surroundings. Now, the first law of thermodynamics says that energy cannot be created or destroyed. So if we are monitoring the heat transfer, or if we're monitoring the temperature, for example, which we used last class to correlate to energy. If we're monitoring the temperature of the system and it changes, it means necessarily that heat had to be transferred either to the system or to the surroundings. Heat either came in to the system or it went out to the surroundings. So there is this flow of heat energy that can come into the system or it can go out of the system. And what is key here was what the first law actually says. And the first law says that the energy, the amount of heat transfer from the system, plus the amount of heat transfer from the surroundings must be equal to 0. In other words, one is exactly equal to the other. If the one gains energy, the other must lose exactly that same amount of energy. And this is a fundamental concept that we will make use of over and over and over again. And so if we can calculate any one of these things, we can determine the other. And we don't even really need to stop at 2. I could have several systems as long as they're contained within some area or some container. The heat transfer that can go back and forth between all of them ultimately must add up to 0. Because whatever one gains, the other must lose. So we can make use of this to help us understand reactions. And it's critically important for us to understand the direction of heat flow. So let's think about that just a little bit. What you're looking at now is a reaction about to be performed. And in this case, specifically, it's calcium carbonate and sulfuric acid. And when we mix these two compounds together, you'll see that a lot of heat is given off. The temperature of the system increases rather dramatically. So the question I would propose to you at this point is, which direction is heat flowing? Is the enthalpy of this system greater now than it used to be, or is it less than it used to be? And this is a tricky question. It's something that students often don't think about. But the answer really has to do with the fact that it's hot. If the temperature is going up, then by definition, it is leaking that energy out. It's going into your hands or into the surroundings or into the thermometer or all of the above. So in a reaction like this, where we see the temperature going up, that is indicative of energy actually leaving the system. We can indicate that diagrammatically like this. Now this is a different reaction, but nonetheless it's the same basic idea. If we mix some compounds to produce products, and we notice that the temperature goes up, what it necessarily means is that the enthalpy must have gone down. In other words, these products from an enthalpic perspective are actually more stable. They're lower in energy. So where did all that energy go? It left the system as heat. And this is back to the first law of thermodynamics. Because we felt heat coming out of that system, that heat energy had to come from somewhere. Where did it come from? It came from the system, and it left the system. So the change in enthalpy in this scenario is less than zero. Enthalpy has gone down. And this is what we refer to as an exothermic reaction, for reasons that I think are self-explanatory. Heat is leaving or exiting the system. Therefore, it is exothermic. And exothermic reactions are signified by negative values for their delta H. Now take a look at this reaction. This is a reaction of barium hydroxide and ammonium chloride. It isn't important that you know or are familiar with those compounds, but as they react, the exact opposite things happen. This is a particular reaction that is famous for demonstrations in chemistry classrooms, and what you do, as you can see here on the screen, is you perform this reaction in a beaker, and you put that beaker on top of a wooden block that's wet. There's some water on top of that wooden block between the beaker and the block. And so as you mix and cause this reaction to progress, you'll notice that the temperature drops dramatically. So dramatically, in fact, that it actually goes below zero. And so all you need to do is keep reacting this for a few more minutes, and sooner or later you'll notice that the water actually freezes. The beaker freezes to the water. So it's a fun little example, but importantly, it demonstrates to us that not all reactions are exothermic. Of course, we can have endothermic reactions as well. And here's a schematic of that process, this time with the correct reacting species. Our barium hydroxide and our ammonium chloride produced a dramatic drop in energy. So imagine you were holding that beaker, you would feel it very cold. What does that mean? That means that heat is being drawn out of your hands. It's being drawn out of your hands and into that beaker or into the system. In other words, it's taking in energy as best it can. And the way to schematically understand that from an enthalpic perspective is that the enthalpy of those products must be greater than the enthalpy of the reactants because it's taking in that heat energy. And in this particular case, taking in a lot of heat energy. So my enthalpy goes up, and therefore my enthalpy change is greater than zero. Okay, and this is an alternative case. This is what we refer to as an endothermic reaction, not endothermic reaction. In other words, heat is coming in. And it's important to know that endothermic versus exothermic reactions have very different outcomes. All right, so we understand the exothermicity or endothermicity of a particular reaction as its ability to give off or take in heat, respectively. But how are we actually going to measure this? Well, we're going to take advantage of the first law of thermodynamics. And what we're actually going to do, and there are several ways to do this, but the way I'm going to show you today is by using a special instrument called a calorimeter. Now, this particular calorimeter is known as a bomb calorimeter, and I'm showing you a schematic diagram of it right here, but the real important part is the cylinder on the inside, which is where our reaction will occur, and you'll notice that that cylinder is sitting in a chamber filled with water. Now, you'll recall last class we talked very precisely about measuring energy changes for a pure substance like water. If water heats up by any amount, we know very well how to calculate the energy that must have been put into that water, right? We used the equation that states that Q at constant pressure is equal to mass times heat capacity times delta T. So if we know the heat capacity of water, which we do, and if we know the mass of the water in this particular instrument, which of course we can, and if we measure the temperature change of this water due to the fact that a reaction is occurring inside this chamber, then we know that this particular amount of heat, which we can calculate very readily, must be exactly the opposite of whatever the heat change was of the reaction on the inside. In other words, this is our system and this is our surroundings. We are controlling both, and we can use the first law of thermodynamics to tell us that the energy heat transfer of the system plus the heat transfer of the surroundings must be equal to 0. In other words, they must cancel with one another. And so we just need to take that into account and do a little bit of math to figure this out. Now, the other components of this calorimeter are really a function of the fact that in a bomb calorimeter, what we're actually doing is performing combustion reactions. So in particular, this is an instrument that's useful for measuring the enthalpy change of a combustion reaction. And how it works, as I've indicated so far, is that we would put our sample inside this chamber, which is known as the bomb cell, and we would fill this chamber with oxygen under pressure because oxygen is required for combustion. We would attach a fuse wire to a couple of different ends of an ignition box, which really just passes a charge through this bomb cell. And we have the pool of water that this bomb cell is sitting in being stirred continuously so that there aren't any hot spots or cold spots. And then we simply monitor the temperature over time. So by pushing this button, we could ignite our sample. The combustion reaction would then proceed, eventually heating up the water on the outside, and we measure our temperature change. And after applying the first law of thermodynamics, we can then determine exactly the energy that was transferred out of this particular system. And if we know how much fuel we had, whatever that fuel may have been, some sort of hydrocarbon or really any type of solid substance that you might want to combust, if we know how much was in there, then we know exactly how much energy was given off per gram or per mole, whatever it is that we put inside. So this is precisely how we measure these energy changes in the context of a combustion reaction. Of course, we can harness the first law to measure the enthalpy change of reactions of all different types, but this one is particularly useful for combustion. So let's try a particular example. Suppose you wanted to measure the energy content or the enthalpy of combustion specifically, and I'll indicate that with a COMB at the bottom of my enthalpy term, of the reaction that combusts sucrose, some sugar, right? Something that you might easily ingest. Sucrose has the chemical formula C12H22O11. So this is sucrose. And suppose we had a 10-gram sample of sucrose. And suppose we wanted to put it inside a bomb calorimeter and push the button, let it go, and measure the temperature change that happened inside that calorimeter. So suppose we did that. And suppose we measured that temperature change and it worked out to be something like 14.6 degrees Celsius. So this would be the amount of temperature change. Suppose the calorimeter was, somewhere around 20 degrees and then it went up to 34.6, right? So suppose that's what happened in this particular circumstance. Can we use this data to figure out what the enthalpy of combustion for sucrose is? That's really the challenge here. And so we'll use the first law of thermodynamics to do this. We know that the energy change associated with the system plus the energy change associated with the surroundings is equal to 0. And we can think of this in a number of different ways. We can rephrase it. We know that the first law is true no matter how we write it. And one way that's somewhat useful to write it is, what if we said, well, there's going to be an energy change associated with the reaction, with the combustion reaction. And by the way, that's actually what we're looking for right here. This is, quite frankly, the energy change associated with the reaction. But that reaction is going to be interacting with the water that it's in, right? It's sitting in water. And that whole thing is sitting inside a calorimeter, the bomb calorimeter. And so all of these things can shift and change energy back and forth amongst one another. But if they do, it really doesn't matter because the net change is overall zero. This is the first law of thermodynamics. Now we know what most of these things are equal to because we've already spent a class talking about energy changes for processes where temperatures change, right? M times C times delta T, where C is the heat capacity of the substance. So it's really just an exercise of figuring out what the heat capacity of the substance is. Now for water, that's pretty easy. We know what the heat capacity of water is, and you might be tempted to just use that. But don't forget that the water was inside a calorimeter. So this is our calorimeter and the water is inside, so the water can gain some energy and maybe pass it on to the calorimeter and vice versa, and so there is a bit of change there. So what we generally think of is lumping the water and the calorimeter all together, because you can consider that the water is in a sense part of the instrument. The calorimeter includes the water. It doesn't exist without it. And the water would not be useful without the container that it's sitting in. So they're usually considered one and the same thing. So that would allow us to essentially combine these two and consider them really as just the heat change associated with the calorimeter itself. So we can combine these and just talk about the heat change of the calorimeter. Keeping in mind that this, I don't necessarily mean that these are the same thing. I mean, there's the calorimeter, the metal instrument, then there's the water that's inside. And I'm saying we could consider both of those as being just the global calorimeter itself. And of course, the Q of reaction, that is the delta H that we're actually looking for right now. So I can write delta H of combustion or delta H of reaction. I can write it however I want, but there we go. So either way, though, I know that if I put those two together, it's equal to 0. And so the enthalpy change for this reaction, if I move my heat change for the calorimeter over to this side, I can easily see that the enthalpy change for this particular process that occurs inside this calorimeter is really just minus Q of the calorimeter. And Q of the calorimeter would again be MC delta T, like we've talked about before. And what we often do with an instrument, right, this is a calorimeter, the mass of the instrument, so what we might be inclined to write is, we'll put a minus sign there to carry that through, MC delta T, we might be inclined to think of the C as the heat capacity for water, and we might be inclined to think of the M as the mass for water too. But let's not forget that we've actually combined the water and the calorimeter all together. And when we're performing these experiments, the same amount of water always goes in the calorimeter. And so the mass of this whole system, the mass of the outer shell and the water on the inside, never changes. And so this is a known mass, and that calorimeter constant, or the heat capacity of the calorimeter, would also be known. And so often these two are just combined. Often we'd take the mass of the calorimeter and the heat capacity of it, and we would just multiply those because they never change. And so what you'll often see this written as is minus uppercase C now of the calorimeter times delta T. So this is now referred to as a calorimeter constant. And it's a characteristic constant that describes effectively the heat capacity of this calorimeter. And so now it truly is a system surroundings thing where the system is the reaction and the surroundings is the whole calorimeter itself. And so as long as we know the heat capacity of the calorimeter, or sometimes referred to as the calorimeter constant, we can predict precisely what this enthalpy change is. So let's do that. In this case, we would need to be given the calorimeter constant, but experimentally, you can simply calibrate these. So this is usually done with a standard sample, some sort of, usually it's benzoic acid or some tablet that you have a standard combustion enthalpy for. You know very well what the combustion enthalpy is. And what you do is you put that inside your bomb calorimeter and go through the experiment and determine what the calorimeter constant would have had to be to give you the answer you knew you were expecting. So that would have been a calibration exercise. So suppose we had done that prior to this particular sucrose experiment, but we could determine that the calorimeter constant was 11.3. In this particular problem, we're simply given this. So we know that our calorimeter constant is 11.3. We also know that our temperature change, we stated that earlier, is 14.6 degrees Celsius. So really, there's not much to be done here. Down here in this bottom left corner, I'm just going to solve this problem by rewriting my equation that I got from the first law. And I know that this is minus my calorimeter constant, which is 11.3 kilojoules per Kelvin, and I'll multiply that by my temperature change. There might be a slight little trick to this where you might be wondering whether I should keep degrees Celsius or convert this to Kelvin, but don't forget, temperature changes. It doesn't matter if it's Celsius or Kelvin, right? That's because 1 Kelvin is the same as 1 Celsius. So there's no need to add 273 to this. In fact, if you did, you'd be way off. This is a difference in temperature of 14.6 degrees, and therefore it is also a difference in temperature of 14.6 Kelvin. Those are equivalent. And so if we multiply these two numbers, you will get an answer of minus 165 kilojoules. In other words, there was 165 kilojoules given off. Notice the negative sign. This is an exothermic reaction, and that makes perfect sense because the temperature inside the calorimeter went up, right? The reaction gave off heat energy. The reaction gave off this much heat energy, which caused the calorimeter to rise its temperature by 14.6 degrees. So this is an exothermic combustion reaction with precisely this amount of energy content, 165 kilojoules. So there was 165 kilojoules of energy in 10 grams of sugar. That's how we figure out the energy content in foods. Now, sometimes we would want to report this in other units. So for example, maybe we wanted to know how many kilojoules per mole of sucrose, or how many kilojoules per gram of sucrose. But that's not so hard since we know how much sucrose we were given in the first place. So let's get rid of some of this writing over here on the side, and let's think about expressing this energy change in other unit systems. So for example, we may be interested in the per gram value of my delta H of combustion. So per gram, I know that I've just given off 165 kilojoules of energy, and that was contained within 10 grams. Therefore, I know that there's minus 16.5 kilojoules of energy for every gram of sucrose. And that's really all there is to it. If I instead would be interested in maybe kilojoules per mole, there's a common thing to do, then I would need to know how many moles I actually had. I know that I've got 10 grams of sucrose, so I'd have to work out the molar mass of sucrose, which I can do because I'm told how many carbon atoms, how many hydrogen atoms, and how many oxygen atoms I have. And if I tallied all of that up, I'd get 342.30 grams per mole. So my 10 grams divided by 342 tells me that I've got 0.02921 moles of sucrose. So if I go back to my original delta H of combustion numbers, I know that my combustion enthalpy that I originally calculated was a total of 165 kilojoules, but that's per 0.02921 moles, which gives me a total of minus, and I'm going to have to zoom in here to get it on scale, minus 5,648 kilojoules per mole. All right, so that's a relatively large number per mole, but this is essentially how it works. We can work out the enthalpy of combustion taking advantage of the first law of thermodynamics, which says that all the energy given off must be the opposite of the energy absorbed by the calorimeter. I figured out the energy absorbed by the calorimeter using the calorimeter constant, which was given in this case, and I determined that I had 165 kilojoules of energy given off in this reaction. Then I converted that to kilojoules of energy per gram, and then I converted that to kilojoules of energy per mole. All are very common unit systems in reporting the energy or the enthalpy change of reactions. But this is how it's done. You take advantage of the first law of thermodynamics, you perform that reaction inside some sort of device that allows you to capture heat energy, a calorimeter per se, and then by measuring the heat energy given to the calorimeter, you know that the energy given off by the reaction is exactly opposite to that. And so this is how the energy content is measured in foods. You take your fuel, your hydrocarbon, whatever it is, sugar, maybe it's a Cheerio, and you put it inside your calorimeter and you do the experiment we described today, and you can calculate precisely how many kilojoules of energy or how many calories of energy, which is typically reported on these food labels. And if you're wondering, well, is this really transferable? For the most part, yes. Think about what your food actually is. They're hydrocarbons for the most part. And when you consume them, what else does your body do? Your body breathes oxygen, doesn't it? And what does your body produce as a result of that respiration? You breathe out water vapor and carbon dioxide. Anybody who knows combustion reactions will tell you that hydrocarbon in with oxygen and you produce carbon dioxide out with water vapor. You are essentially a combustion machine for your food. So a bomb calorimeter is the perfect instrument to measure exactly how much energy that food gives to you.